right, so we have our next guest for story time. This is Dr. Ian Cash, who is an associate professor at UIC in the Department of Computer Science. Um, all of the faculty that you're seeing here, well, not Satya, but uh, Dr. Cash, Dr. Party, and I all started the same year. So we're kind of like a faculty class together. We actually have those. But so Dr. Cash, he works in the area of economics and, he works in the intersection of economics and computer science, and a lot of it is machine learning. So he's going to be telling you a little bit about some really interesting applications of graphs that really supplement, many of them that I listed during our graphs weeks. This includes graph coloring, which is fun, and minimum spanning trees and other graph applications. So enjoy as you listen to some of the work that Dr. Cash has done in his research that applies directly to things that you now know all about.
All right, hi everyone. For this video, we have Professor Cash here to join us and talk to us a little bit about some of the work that he's done in the area of data structures.
Hi everyone. I work at the within artificial intelligence as well as applications of computer science and economics, and a lot of the work I do involves graph data structures in one way or another. So I'll tell you about a couple of the ways kind of graphs have shown up in my research that have important real-world applications. And if you're interested in these things, I tend to teach CS 411, artificial intelligence, and CS 407, which talks about economics and computation questions, and I talk more about these examples in those courses. So kind of the first place I want to tell you about is when you use graphs to solve what are called matching problems. So there's lots of important markets out there in the world where there are people and there are things that those people want. And so, for example, you might have medical students that are finishing up medical school and want a residency at a hospital. You might have students that are finishing high school and want to go to college. You might have people who are very ill and they want a new organ so they can have a transplant. So you have all of these things out there in the world where there's kind of people and things they want. And so a natural way to model these problems is as a graph where you have kind of two different sets of nodes or vertices in your graph, one set representing all the people and another set representing all of the objects you want to assign them to. And then what you want to do is somehow compute a good matching of those things up. And in some applications you care about just getting the biggest one you can. In others, you might have weights on the edges, and you might care about the weight of the matching that you produce, sort of the total value of all of those things you've created. So I'll tell you about sort of one particular example I've looked at in my research, which is, so kidney disease is a major problem. And so there's many, many people who have a kidney that fails, and we can keep you alive for a while after your kidney fails through dialysis, but it's not very pleasant and it's not good for your long-term health. So we kind of try to get people transplanted with new organs as soon as possible. And some of those organs come from people who have died, sort of cadaver organs, and there's a waiting list process for that. But sometimes people find a friend or a family member who's willing to donate an organ to them. Because you have two kidneys and you only actually need one of them. But there's a catch about this, which is, if you sort of think back to biology, you might remember learning about blood types and things like that. You can't necessarily have a transplant from any arbitrary person. Your immune system might reject an organ that you're offered because it doesn't just, sort of the proteins on the organ don't match up with what your body expects. So as a result, there's sort of a compatibility relationship among people. And so you can think of it in this problem, the graph is capturing those compatibilities, or how likely this transplant is to work out. And so you have a goal of doing this. And one of the clever ideas people have come up with sort of over the past 10 or 15 years, which has saved a lot of lives, is the idea with you might have somebody who's willing to donate a kidney to you, but isn't compatible with you. And there might be somebody else who has somebody willing to donate a kidney to them, but also is incompatible. But effectively, you could swap these kidneys. You could have the person who is willing to donate to you donate to this other person, and the person willing to donate to that other person donate to you, so that everybody kind of donates a kidney, everybody gets a kidney, and everyone is happy, and you enable many, many more transplants and a much better quality of life for people. But of course, now you have this kind of optimization problem under the hood, and people have put a lot of work into thinking about the algorithms used to solve this problem and kind of their, the how to create the most benefit for society. And so that those sorts of issues are one thing that I have worked on.
That's really cool.
Yeah, I think so as well. So another application that I like is an example of graph coloring, which I think you've talked about. And so the application here is that you all have many wireless devices of various sorts, right? You have cell phones, you have television getting broadcast over the air, you have even things you don't necessarily think about as intentionally broadcasting that use up spectrum, like microwaves. There's all sorts of electronic devices that sort of emit radiation, and that radiation can interfere with the ability of things to communicate. Sort of if two devices are sort of sending out radiation or trying to communicate in the same part of the spectrum, they interfere with each other, and your Wi-Fi call drops and things work. So you want to try to find ways to get people communicating on different channels. And so you can think of this as you can build a graph of all of the people who wish to communicate or the various spectrum, and you can put edges between two people that wish to communicate if they will interfere with each other if they are talking on the same channel. So for example, if all of us are trying to use our cell phone and we're all speaking, we're all sort of all working with cell phone towers from different companies that are in the same area, we want to make sure that those are on different channels so they don't interfere with each other. Similarly, if you have two different TV broadcast towers, someone living in between those towers might have interference and not be able to get a good signal. So you have all these optimization problems around who should use the spectrum that you can phrase by drawing what's called the interference graph, the structure of the graph that captures the structure of this interference, and then solving a graph coloring problem to determine who should go on what channel. And so often people look at different greedy algorithms for things like this. Sort of in my research, I've looked at how you can use this when people are actually able to share channels, which adds sort of new complications to the problem. And sort of other people in their research have looked at the design of the billion-dollar auctions that were, for example, recently used to change around what channels TV stations were broadcasting on by the FCC, sort of raise billions of dollars in revenue and free up lots of spectrum for wireless carriers to make everyone's phones work better. So those are two applications of graph data structures in my research.
That's really cool. Thanks so much for stopping in and chatting with the students. I think it's really cool for them to be able to understand so much about the beginning of all of these new problems just from taking the one data structures class. So thanks so much for coming.
You're welcome. Have a great day.
Yep. Bye.
Bye.